the size of the class number. And so this point P has many conjugates. Also, these class numbers are not very large. That upper estimate is effective. And also, the Veil height, the singular moduli have a quite small Veil height. This is logarithmic Veil height in terms of the discriminant. And so the multiplicative relation is somehow controlled by this complexity. The size of the, what have I called them there? The size of the, I haven't called them there, the BIs. If you've got, so the alpha i's here will be the singular moduli, and we want to control the size of this multiplicative relation. How big are the BIs? And by a result, well, it appears in this paper of Lower and Natter, but they attribute it to you, that you can bound the size of a multiplicative relation in terms of the Veil heights and the degree of the fields and so on. The degree of the field here is bounded above by that complexity, and all the heights are bounded by the epsilon power. So altogether, the AIs, which should say BIs, I've just changed the size of those AIs is bounded by some fixed power, depending only on n of this complexity measure of the tuple. So now we come to counting rational points on definable sets. So this X is uniformized by the n-fold product of the upper half plane and the complex plane, where you, with the J function operating on the first n coordinates and then the exponential function on the next n coordinates. And they have the standard fundamental domains. So for the J function, we saw this in the last talk. And if you take the pre-image of V and intersect it with the fundamental domain, then this is a so-called definable set in orthogonal structure. We behave classes of real sets that we can say something about the rational points on them. And so is this set that I've called Y, where I've taken this set Z and I add some more real coordinates that parameterize linear relations from the exponential side. That's where the multiplicative relation will lead to rational points in the T's. Yes. So this set Y is a definable set, and so is its image Y prime, where we forget about the U variables, because there'll be no rationality. You see, when you have one of these multi-modular tuples, when you pull it back up here to Z, the Z coordinates here will be quadratic. So that's the kind of rationality property that we can control. And the T here, we're going to get rational points here because of the multiplicative relation. But the logarithms of those points are not going to have any decent rationality properties, so we project them away. And then we get this set Y prime. This is a definable set. And every multi-modular M tuple gets you a point. Leads to what you might call a quadratic rational point on this Y prime. The Z coordinates are all quadratic irrationalities, and the T coordinates are rational. And now, the fact that the multi-modular tuple P has, if it has complexity delta, then it has a lot of conjugates. So we can apply that Brouwer-Siegel estimate, let's say taking the epsilon there to be a quarter, we'll get at least delta to the quarter power conjugate. And each one of those is going to give us a point in Y prime, which is quadratic rational in that sense. And its absolute height that's multiplied by the result, the fact that the complexity of the multiplicative relation is controlled by the discriminant, that will have some size bounded by some power of delta. And now, very general theorem, mine with Alex Wilkie about counting rational or bounded degree algebraic points on a definable set, says that for any epsilon, there are at most some constant depending on epsilon, and the set T to the epsilon rational points up to height T. This is the absolute height of the point. Just for a rational number in lowest terms, that's the maximum of numerator and denominator, and for a quadratic point, it's the largest absolute value of the integral coefficient of the minimal polynomial of the quadratic. So this tells us that if there's a point B on this, if there's a multi-modular M tuple on this variety V with a sufficiently large complexity, then there's going to be some real algebraic curve in this definable set Y prime. We found something real algebraic. And then this curve, associated with this curve, of course, is the hyperplane on the T to the N, which, so for every point in this curve, there's an associated hyperplane that intersects the edge. Yes, no, it could be higher dimensional, but at least it contains a semi-algebraic curve. That's all I can use. Yeah, that's all I need, because I'm going to complexify the parameter in that curve, and now I get a complex algebraic set. If I get a complex curve and the corresponding planes, so that will be a hyperplane, so that will be an n-dimensional complex algebraic subvariety up in this Hn cross Cn, which intersects the pre-image of V in a set of complex dimension 1. Now, the pre-image of V has complex dimension n, and it's sitting in a 2n-dimensional ambient, so for it to intersect this algebraic thing W, which is dimension n, in dimension 1 is again atypical. But it's an atypical intersection of a different kind. And now we're in functional transcendence land, because we've got a kind of exceptional intersection of something algebraic, with the pre-image is something algebraic under the J function and the exponential function. So this here now on the up here is Chenwell theorem, axis theorem, the functional version of the Chenwell conjecture, which this is just axis theorem, actually written in this complex form. This is something. Yeah, no. So here we're taking just the graph. So here gamma is the full graph of exponentiation. This is axis theorem. I mean, axis theorem is usually stated in the differential field, but it's actually, this is something that Jacob, well, I think, realized it's completely equivalent to this complex formulation. So here gamma is simply the graph of the n-fold Cartesian product of exponentiation. And this V is not the previous V. This V is an arbitrary algebraic variety in there. And we simply intersect the graph of exponentiation with this variety V. And then the theorem says that if you take a component of that intersection, then the dimension of that is always typical, unless that last line happens. So the dimension is always the dimension of gamma plus the dimension of V minus 2n, which is then V minus n, unless this projection of A on the, well, it doesn't matter where you project it, actually. It's contained somewhere in a proper weakly special subvariety. But in Cn, it says that there's a rational linear relation that holds on A. And another way of saying this that makes it look more like Chenwell's conjecture is that if you consider on this intersection A the various functions, the zi and the e to the zi, the dimension of V is the transcendence degree of all those functions, and that should be at least n plus the dimension of A, unless the zi's are linearly dependent over Q mod C, meaning that there's some rational combination of z's which is a constant. All right, and so if you really want to go to the differential formulation, the dimension of A is actually the number of independent derivations on this differential field. So this is axis theorem. And so the kind of application here is actually a weaker version that one is interested in, the so-called two-sorted version, where you separate the Cn and the C star to the n. So now we consider a W in C to the n and a V in C cross to the n, and an A in their intersection. And then if you apply the previous theorem with this V being V Cartesian product W, or actually I should say W Cartesian product V, then you get this equation. So the dimension of A is, the intersection is always typical in a dimensional sense, unless A is contained in a proper weakly special subvariety. And another way of saying that, because you can then reapply axis theorem inside the weakly special, and you can keep going like that until you find a weakly special subvariety in which that intersection is not atypical anymore. So another way of saying this is that, is what I've written there, that you can eventually find a weakly special subvariety U prime, which contains A, and the intersection is no longer atypical. In other words, the defect, the difference between x prime, and which is the image of this U prime will be your smaller ambient x prime. W prime is now the, well, that'll be the intersection of W with U prime. This intersection is now no more atypical because it's of the same codimension as V prime is in its ambient. Anyway, I think so now what the rest of this analysis really depends on is an analog of this Chenwell as a modular function, which again is a recent joint work with Jacob Zimmerman. It's exactly the same, well, in this version it's exactly the same theorem, but for the modular function. And there's even a version involving the derivatives. For J and J prime and J double prime, these should all be independent. J satisfies the differential equation of order 3, but for exponential function this is just order 1. So this is an analog of axis theorem, and again it has a number of ingredients which include some complex geometry, basically to show that this component goes through very many fundamental domains. And then there's again some point counting in O-minimal structures where you count those fundamental domains as a rational point on a certain definable set. And then there are some other ingredients, some monodromy and some also, well, complex geometry in an O-minimal setting. So there are some powerful results of Picozzo-Sarchenko, things like Chow's theorem, but with slightly different hypotheses, definability in these O-minimal structures. Now from this, so now we've got axis theorem, and we've Chenwell for the exponential and for the J function, and for this we can deduce a two-sorted version for this mixed thing, the mixed modular multiplicative situation, and it has the same implication that if you have